Alright, ladies and gents, so welcome back. So we're going to pick up with covalent bonds today. So last time we were talking about ionic bonds where atoms are attempting to fill their valence shell by either accepting or giving away electrons. Covalent bonds, on the other hand, are going to occur when one or more electrons gets shared between atoms. So think of ionic bonds kind of like that kindergartner who hasn't really learned to share, and so one of them is taking the toy, or in this analogy, the electrons, and somebody's losing it. Covalent bonds are those really nice little kindergartners who have learned to share their toys. Alright, so covalent bonding, I've got one or more atoms that are going to share those electrons. So these electrons are going to spend time around this nucleus, this nucleus, this nucleus, regardless of where they started originally. So they travel around all of these nuclei and they're sharing those electrons equally. That's what's holding a covalent bond together, the ability for those electron clouds to essentially overlap. So there are not necessarily charges with covalent bonds. Okay. Now we can classify covalent bonds based on how many pairs of electrons get shared. So if I'm talking a single covalent bond, something like the hydrogens here with this carbon, then they are sharing a single pair. So one of those electrons is coming from the hydrogen, the other electron's coming from carbon. And you'll often see them with just these single lines as a way to delineate a diagram of what a single covalent bond looks like. So a single pair, so a total of 2 electrons are getting shared. In a double bond, however, alright, now I've got 4 total electrons that are getting shared, so 2 originally came from this oxygen, the other 2 came from this, and you'll often see it as 2 lines, kind of like an equal sign. Or I can actually have up to a triple bond, which is what's going on here in this nitrogen model. So these 3 electrons came from this nitrogen, the other 3 are coming from here. I've got 3 total lines now, and so we're sharing a total of 6 electrons. So in covalent bonding, just like ionic, the end goal is for these atoms to have a full valence shell, which for most elements is a total of 8. And so we can share 2 electrons, and that may be enough to get everybody in the molecule happy and have a full valence shell. Sometimes it may mean we're sharing a total of 4, or maybe even all the way up to 6. Big thing here is to keep in mind that unlike the ionic bonding where I had somebody gaining electrons, as a result gaining a negative charge, plus an atom that was losing electrons and then having a negative charge, there are no charged atoms going on in covalent bonding. They're neutral atoms, and they're going to come together to form these molecules in covalent compounds. And oftentimes you'll see molecules are sort of this term we utilize across the board, or sometimes it's more specific to actual covalent molecules. We won't get too in-depth or too nitpicky about where you use that term, so long as you're talking at least about a atom joined to another atom. Alright, but a lot of times you'll see that molecule term used really strictly with the covalent compounds, and we're talking about it as the smallest unit of that covalent compound. So while I can break apart those atoms, they start to lose those properties of that compound in and of itself. So just keep in mind if you see that term specifically linked to covalent compounds, that's not uncommon, but we won't get super nitpicky about it. So let's talk about how these covalent compounds end up getting formed, and we'll use water, which is going to be a big molecule that we talk about a lot here in biology, as an example. So here I've got my oxygen molecule, and if you don't have your periodic table out, you may want to pause the video and grab it. So oxygen in and of itself alright, has 6 electrons to itself, 6 valence electrons. Remember, the whole goal is to get to 8. Each hydrogen has 1 valence electron, and remember, he's one of those caveats. He's in that very top row, so he only needs 1 more electron to get to be like helium and be stable. So what ends up happening, well, this electron may have originally been hydrogen, so he's going to share those electrons with oxygen. Oxygen's going to share back, and so essentially they're sharing this pair right here. So hydrogen now has the 2 that it needs, and now oxygen's up to 7. Well, the same thing's happening on this side. So this hydrogen may have originally come from, or this electron, may have originally come from this hydrogen. Oxygen's got its now 7 that it's sharing. So we share this pair. So now hydrogen's stable with the 2 it wants, and now oxygen has the total of 8 that it wants in its valence shell to be stable, happy, and have that sort of noble gas configuration. So you've got some examples just like we did with the ionic bonding. We're going to go through and do some with covalent. So I'll walk you through a few, and then I'll let you do some practice on your own. So if we take a covalent bond and we're looking at 2 chlorine atoms, alright, so this would actually be a diatomic molecule. Take a look at your periodic table. Chlorine's in column 7, so 7 valence electrons, and because we've got 2 of them, same deal, alright? So they both need 1 additional electron to ultimately get to those 8 valence electrons that they want to be stable. So here's where it gets a little different from what we did with the ionic bonding. Unlike ionic, where we wanted to show those open and closed circles so we could see the transfer of electrons, covalent bonds don't transfer. So we're just going to use closed dots like we were doing when we originally learned how to do our dot diagrams. So I've got 2 chlorine atoms, both have 7 valence electrons, and so they would look something like this. Next step then is to determine who's going to share how many electrons with who. So each chlorine atom, we already determined, has 7 valence electrons in its outermost orbital. The ultimate goal is to have that orbital full, right? So that means each chlorine is going to need 1 additional electron to get to that octet set that it needs, or the total of 8. So that means that each chlorine is going to have to share a single electron with the other chlorine in order to get the 8 that they both need to be stable. Final step is to draw the dots so that you can show the shared pairs. Something I'm going to encourage you to do is to consider picking up a couple of different colors of colored pencils and doing 1 atom each in a different color, and it hopefully will make it a little easier for you to see where the electrons are getting shared from. Alright, so the other thing I'm going to encourage you to do is to take a look at doing something like this. So let's just say I'm going to use blue for one of my chlorines. So here's my original Cl, right? And I'm going to take all of those paired electrons that they originally had, and I'm going to put those on the outside. So here's 1, 2, 3, 4, 5, and 6. I'm going to place the unpaired electrons in the middle then. So he had 1 unpaired electron, so there he goes. Alright, same deal, but now I'm going to come and I'm going to do the other one. So I'm going to place them next to each other. So here's my other Cl. Okay, same deal, place their already paired electrons on the outside. So 1, 2, 3, 4, 5, and 6, and then go ahead and place that unpaired electron there in the center. So now that means that this chlorine, alright, sorry for the bad circles here, are the total of 8 I need, his original 7, so 1, 2, 3, 4, 5, 6, and 7, plus now it's got 8 from this chlorine. My other chlorine, same deal. Alright, so he's going to share those, right? So it sort of ends up looking like a Venn diagram. What's common in the middle is what they're sharing, and then what's on the outside is sort of what was inherently theirs to begin with, and they don't need to share, although be careful with that, because remember I said all of these electrons are now fair game to travel around the nuclei of both atoms, and so they will, and that's ultimately what holds this all together. Okay, so hopefully that makes sense. And so there's kind of what it looks like. Let's do another one. So I've got carbon and 4 chlorines. Well, carbon's in column 4, so 4 valence electrons. We already just looked at chlorine. They've got 7 apiece. Alright, so if I draw my diagrams before anything happens, there's what my carbon looks like. And I gotta draw all 4 chlorines, so there they are. Okay. So carbon, we said, has 4 valence. What does that mean? That means it needs a total of 4 more in order to fill its valence shell, right? We need to get to 8. So each chlorine, it's got 7. We determined in the last example, and it will hold true here as well, that each of them needs 1 to fill its valence shell. So in order to make this function and fit together, each chlorine is going to share 1 of its electrons with carbon, while carbon is actually sharing all 4 of its valence electrons, but only 1 electron with each chlorine itself. Okay. So how do I end up drawing this? Well, same deal, right? So I'm going to take one of those molecules, one of those atoms. Alright, let's just say I'm going to start with carbon. Alright, just a hint, carbon tends to end up in the center of things, by the way. And it didn't have any paired electrons, so I'm going to throw the same dot structure that we had on the previous, before anything happened. I'm going to throw them all there. But then I'm going to come in and I'm going to take my chlorine. Let's take one of them. Alright. It did have paired electrons, so I'm going to throw those guys on the outside. So 1, 2, 3, 4, 5, and 6. And there's where I'm going to plug in that 7th valence electron, right? So he now has all the 8 that he wanted, thanks to that 1 that it's sharing with carbon. But I have a total of 4 of these, so same deal. I'm going to come over and do the same thing. So here's another one. So 1, 2, 3, 4, 5, and 6 that it already had, plus 1 more. And now this guy's got the 8 that he wants. Alright, and you'll do the same thing with the other 2 chlorines that you've got hanging out there. Alright, until you end up with something that looks like this. So I want you to pause the video, take a couple of minutes, and try to finish the last couple of examples yourself, and then come back to the video and go ahead and check your answers. Alright, so hopefully you were able to walk through this. These do get a little bit more challenging, so hopefully you were able to figure them out. If not, let's walk through it together. So carbon we just dealt with in the previous example, so column 4, 4 valence electrons. Oxygen ends up in column 6. I've got 2 of them in this particular example, and so those oxygens each have 6 valence electrons. So before anything happens, there's my carbon again, and my oxygens end up looking something similar to this. So carbon's got 4. We established that it needs 4 more. Oxygen has 6. In order to get it to 8, that means it's going to need 2 additional electrons to fill its outer shell. So what ends up happening is that oxygen is going to share 2 of its electrons now with carbon, Well, carbon shares a total of 4, but 2 with each. So hopefully you started to see a pattern here where it wasn't going to be as cut and dry and simple as a single covalent bond, which is what we were dealing with in the 2 examples that we did together at the start of this. So here instead, alright, let's take one of those oxygens, alright, and I said stick your paired electrons on the outside. So 1, 2, 3, and 4. It had a total of 4 electrons that were already paired off, already filled. But it also then had 2 that didn't connect to anything. Alright, so that's where I'm going to put those guys. I'm going to do the same thing to the other oxygen, but on the other side. Remember I mentioned to you, carbon often ends up in the center, and that's what's going to happen here too. So 1, 2, 3, 4 that had already been paired. Oop. Let's fix that, make that a little clearer. Alright, and then the 2 unpaired electrons there. Now carbon's going to end up in the middle of all this. And carbon didn't have any shared paired electrons at all. But remember, carbon's going to need to share 2 electrons with each oxygen in order for oxygen to get the 8 that it needs. So where are they going to come from? Well, here's 2 of them from carbon, right, because it started off with 4. And there's where the other 2 go. Okay. And so now I've got carbon sharing all of these guys. Alright, so 2 from this oxygen, 2 from this oxygen to get 4, plus the 4 it originally had, it now has 8. This oxygen is now sharing all of these, the original 4 it had, plus these 2 that it's sharing with the carbon that belonged to it, so 6, plus the 2 it's getting from the carbon, so there's your 8. And same deal with this guy over here. Okay, and so you end up with something that looks like that. Okay, so I made a double bond. Alright, and if I were to sort of shorthand this, I'd have two lines going between those carbons and oxygens. Okay, so hopefully those examples make sense. Alright, so we're going to move on just a little bit more today and talk about not only can I classify covalent bonds as single, double, or triple based on how many electrons are getting shared, but I can also talk about how those electrons are being shared. So not just the number of them, but the actual inherent sharing itself. And so that's where we're talking about polar versus nonpolar covalent bonds. Not every atom is going to share its electrons equally. Okay, so the sharing happens, but it's not happening kind of at the same rate. So we talk about a polar covalent bond as opposed to a nonpolar covalent bond. So nonpolar, if I go back to that kindergarten analogy we started with today, your nonpolar covalent bonds, all the atoms that are involved in the molecule itself have an equal sharing. They're all good at sharing their toys, right? So in this case, they're electrons. So those electrons are going to spend equal amounts of time around the nuclei of every atom involved. A polar covalent bond is somewhere in between being ionic and nonpolar. Alright, so ionic, they completely take, somebody completely loses. Nonpolar, 100% equal share. Polar covalent, I end up in the middle where some atom or atoms in that molecule have a slightly stronger attraction for those electrons. We talk about it as electronegativity. So they have a slightly stronger pull, in which case they pull those electrons to themselves around their nucleus a little bit more of the time, where some of the other atom or atoms in the molecule aren't quite as able to hang on to those electrons, and so they don't spend as much time there. So we talk ionic, it's full charge, right? So the bully versus the poor little kid who got his toy stolen. Nonpolar, completely super sweet, nice kindergarten kids, everybody's sharing, everybody gets that toy at the same amount of time. Polar covalent is somewhere in the middle, where we've got this kid who is learning to share, but isn't really perfect at it quite yet. So while they hang on to that toy for a little longer than they should, they eventually recognize they're supposed to be sharing, and so they do. Another way to think about this might be parents who are divorced versus parents who, parents who are divorced in terms of how much time those kids spend with each parent. Nonpolar, you've got a divorced family, but everybody kind of lives in the same town, and the kids can go to the same school regardless, and so they spend equal amounts of time with both parents in a given week, right? Polar covalent is more like that traditional custody arrangement where you've got the kids spending Monday through Friday with one parent because that's where they go to school and they need to be in that household at all that period of time to make sure they get to school every day. And then the other parent sees them on the weekend because that parent lives somewhere else. Alright, so electrons, or in this case the kids, are spending a bigger portion of time in one house or around one nucleus as opposed to the other. So what ends up happening is that the electrons, where they reside more often, force that molecule now to have partial charges. Okay, and I am going to be a bit of a nutcase about showing this partial charge. So when I look at it, alright, you get this squiggly little S symbol. Alright, and you have to show this, because if you don't, and all you do is do plus and minus, even though I'm going to tell you right now, you're going to see it in textbooks, you're going to see it in pictures, you're going to see it on the internet, it's wrong. Alright, please make sure that you're putting that partial charge in there, because if I just write positive or negative, it makes it seem like they're ions. And that's not what we're dealing with here. So we want to make sure we're really good in being explicit about showing that it's a partial charge, so it's still sharing those electrons. It's just that it's not sharing them equally. So if I come back over here to my water example, alright, oxygen is this big honkin' atom. It's got a stronger ability to hang on to those electrons around its nucleus more of the time than these small little hydrogens. And so what ends up happening, well, this side of the molecule ends up with that partial negative charge, okay, because it's hanging on to those electrons more. The hydrogens, on the other hand, end up with partial positives. Okay, and the reason being, they don't get to hang on to those electrons as much, so their proton, their positive charge in their nucleus, shines through a little stronger, and that's where that positive charge comes from. This is going to become really important when we start talking about water properties. So keep in mind, water is going to be sort of our classic example of a polar covalent bond. Alright. And here's what I mentioned before. So why do I end up with these partial charges, these polar covalent molecules in some cases? It really comes from the ability that is inherent to each atom or to each element on the periodic table, something we talk about as electronegativity. So electronegativity in and of itself is simply a property, a comparative property, that shows how well an atom is at hanging onto electrons. And so there is a pattern that shows up in our periodic table. Elements more towards the right of your periodic table, alright, tend to have a stronger attraction for electrons. The further down you go, the stronger that attraction becomes. And so when I'm looking at atoms that are coming together to make these molecules, if I understand this particular property and this pattern that I see in my periodic table, I can start to make some hypotheses as to whether or not I'm going to end up dealing with a molecule that's polar covalent or non-polar covalent. Now, we're not going to get into anything crazy beyond you really should know water's polar, but just something to give you a heads up, it is something you'll end up seeing in chemistry in the future. Alright, and it's going to become important because those polar molecules are then going to be able to have these additional attractions that happen between their molecules. So just like I have a positive and negative ion with opposite charges and opposite charges attract, well, I'm going to have that similar attraction going on, but now instead of it being between atoms in a compound, it's going to be between molecules in a substance. Something we talk about as intermolecular attractions as opposed to intramolecular, which would mean within the molecule itself. Now, these intermolecular attractions aren't going to be nearly as strong as a covalent or ionic bond, but they will be enough to influence some of the properties that we deal with in these polar covalent molecules. And we're going to see that when we start talking about water properties, because a lot of intermolecular attractions are responsible for the properties we see with water, because water is in fact